What is C made out of? When I say A equals CR, what is C made out of? Independent column vectors. If I took all the linear combinations of all the vectors in C, I would end up with the column space. There we go, that's the connection. So C is a collection of all the independent column vectors. If I took all the possible linear combinations of those vectors, I would end up with the column space. And the only way that AX equals B could have an answer is if B is in A's. I think I heard you say it. So let's take a look here. So I just want to say a couple things, and I'll throw it up into you guys because I didn't bring much tonight. It's all dependent on what you guys want to focus on. So the only way AX equals B, sorry, it should be lowercase b. The only way AX equals B could have a solution is if vector B is where? Dadgummit. Say again? No. Nope. All right, so let's say that I have C is 1, 2, -5, and R is, what do you got, Jeff? 1, 0, 1. Yep. What's the rank of A? 1. Of course it's 1, because what's the rank of A mean? What's rank mean for a matrix?
It's the same.
It's the number of independent columns. The minute I wrote C, you knew there were how many independent columns in A? 1. So you know the rank of A is 1, and the row space, the row R has to have the same rank as C, has to have the same rank as A. Let me stop for a minute. R tells me how to combine the column vectors in C to recreate A. Is that cool? We've done a few things directly about that, yes? The more important thing is, you all agree that C times R is A, because that's the whole idea. The only way that I could have an answer to this, and basically what that would mean is, I want a vector that I can multiply by my matrix, and the matrix will make the vector become this vector. So if I operate on a given vector with my matrix A, it becomes a vector B. Let me stop for a minute. The other way to look at that is, if I have a vector X, and I multiply it by a matrix A, the vector X is telling you the multiples of the columns to use. Yes, that was the column space, the column picture that we did. Let me stop for a minute. So, let me ask you just this straight up question. With what I've given you down there for C and R, can somebody tell me, for this A, whatever A is, we could put it back together, but we're not going to at the moment. Can somebody give me a valid matrix for, vector for B that would make that equation have an answer? 1, 2, -5. Kick ass. Because again, vector X tells me how to combine the columns in A to create the column vector B. So the only way AX equals B can have an answer is if B is in the column space of A. So the column space of A is every single vector, every column vector that A could possibly create. And if I'm saying I want A times something to be B, well, the only way that has an answer is if B is in the column space of A. So if we know that the only matrix, in fact, this is rank 1. So what are the only possible solutions, the only things that B could be, where there would be an actual answer? Any multiple of this guy, yes? Okay. In fact, let's see. So we would be so far a little bit. In fact, if I multiply these together, what does this 1 mean? Do I actually have to like full on multiply, or is there a bit of a shortcut here? Yeah, the first column is going to be 1, 2, negative 5. The second column is going to be zeros. And the third column is going to be 1, 2, negative 5. So this is very obviously rank 1. If you go through, the first column is automatically independent because we don't have anything else to compare it to. So every matrix we ever look at is at least rank 1. 0, 0, 0. That's no good. Right? That's 0 times the first column. It's not independent. And then, of course, the last one is itself, is the first column. So that's why it's got rank 1. So the only possible B. So what I'm going to do, what do I get if I multiply this? Here, you guys give me 3 relatively nice numbers. 2, 3, 4. I love it. I always got to say that because I always get somebody to say, square root of 11, or whatever. When I multiply that out, what do I get? I mean, one way to do it is the dot product way, yes? So let's see what we get that way. 2, 0, 4. 4, 0, 6. Negative 10, 0, negative 20. How does that relate to this? Well, let's see. What did I do wrong? 4, 0, 8. There it is. I probably should look straight down. So how does this relate to this?
6 times.
It's 6 times this. Right? So the only possible vector B I could put for this given A, this CR, the A that I get from CR, which is here, the only possible things I could put here is a multiple of that, because that's the only thing that A can generate. A can generate multiples of 1, 2, negative 5. That's what it generates. How are we doing so far? Okay. This is stuff we've talked about before. This is the idea behind R and C. R tells me how to put together the columns in C to recreate A. So when I multiply A by a vector x, I can see that as x telling me how to put together the columns of A. So the only things that work on the other side must be linear combinations of the independent columns from our C. That's the only way that would work. So what is the only way that I could have? So real quick, with the A that we just had, are there any B's that would have no answer? Is there any vector I could put in for B and there would be no solution?
Yeah.
There would have to be, wouldn't there? Because we just said what the only possible values for B are multiples of 1, 2, negative 5. If it isn't that, if there's a B that isn't a multiple 1, 2, negative 5, will it have a solution when I put it in this equation?
No.
Hell no, because A can't make it. A doesn't have the right parts to make that. It can only make multiples of 1, 2, negative 5. So, if I somehow knew that this equation, different matrix, yes?
Mm-hmm.
So I'm using a little c instead of a little b because it'll get confusing. Same idea of an equation, yes? If I somehow knew that this equation had an answer for every possible C I could put in there. Let me say this again. If I knew this equation had an answer for every possible vector C you could put in, does anyone know what that means about matrix B? It would be full rank. That's the only way it could possibly just make everything. If it's any less than full rank, are there any vectors it could not create? Yes. Yes, right? So this is kind of going the other way. If I somehow know this equation has an answer no matter what C is, B must be full rank. Okay. And if I go one extra step, if B is full rank, is it invertible? And if it's invertible, of course this dumb equation has an answer no matter what. Because then I can just take the inverse of both sides. So what's the answer always? B inverse C. And that's not why, but this makes a complete picture when you realize if B was not full rank, it would not have an inverse, and therefore, I'm not guaranteed to have an answer for everything, for any C I could put in there. Okay, maybe. This is just on my mind for a couple reasons. We're talking about C, we're talking about R, we're talking about A, we're talking about what that has to do with this kind of equation, which is a huge deal for us in linear algebra, this equation. This remarkably simple looking equation. We've talked the shit out of it, and we're not done. There's more shit we're going to do with it. So it was nice to kind of talk about this. There's also a specific homework problem somebody's asked me about that kind of put me in this mindset. So I just want to put that out there. So if you know a matrix is full rank, if you know matrix D is full rank, will dx equal B always have an answer? Yes, there we go. If you know that dx equals B always has an answer no matter what B is D full rank? Yes, okay. Sorry, I just had to do that. Now, the rest of tonight is exceptionally wide open. You guys are just maybe not used to that. I don't know. I will entertain questions from the quizzes, the practice tests, the homework, the book, your brain. Just, hey, we talked about this shit. What if this? Yes? You can ask me anything. And if nobody says a damn thing, I'm just going to start picking some problems out. Because I didn't bring it in. This is just really based on what you guys want to focus on. We could do example problems of whatever. We could talk about a concept. We could talk about a specific homework problem. We could, whatever. You could work on quiz corrections. You could, yes?
Can you go over number 32 in section 2.2?
Where did I put my, there they are. Section 2.2?
Yeah.
32. Oh yeah, okay, this is what we were talking about. Of course, the way he says this is kind of strange. I'm not sure if you guys, hopefully you guys have picked up on what he means by this. Put the matrix U right next to the identity matrix. So remember when we talked about inverses and I showed you at least once, if not twice, we did a 2x2 and a 3x3, if I remember correctly? How to find the inverse of a matrix was we augmented the matrix with the identity matrix and then row reduced. Yes? Because the identity matrix acts like a memory cell. It's very neat. It's like I plug in a USB stick and I just have it memorize all the shit I'm doing backwards. And it's like what it collects at the end must be the inverse because it has all the opposite operations in all the opposite order. So you just have to write this with 1 0 0 0 1 0 0 0 1 next to it and then row reduce. Now, the next exciting thing about this is there's letters in there, but we're freaking linear algebra. We know this shit. We know this happens. Oh well. So like how would I kill the A? Because I want the A dead, yes? The first column looks great. You all with me?
Yeah.
It's because it's upper triangular. Of course it looks great. How would I kill the A in the next column?
Row 2 minus A row 1.
Other way around.
Or, yeah.
A times row 2 minus row 1. Is that cool? And you would do that all the way across. So just to really make sure you guys are with me. And you're like, we lost you when you walked in the room. So if I write U augmented with Jeff, not with Jeff. That is U, I. That's what they mean by U, I. Put U and put an I next to it. Now, row reduce this. When you get to the end, when you get this side to be 1, 0, 0, 0, 1, 0, 0, 0, 1, whatever is here is the inverse. Huh?
And that's the answer.
And that would be the answer. That's all they want, is just what's the inverse. Yeah? And I love this problem because you can't just put it in your calculator. You got A, B, and C in there. Maybe with TI-89, I don't know. Huh? See? Formula? Oh! Yes. Using the, yeah, if you have a formula you could follow that's not this long thing is. Is that okay? That's what they want you to do for this problem. Yeah, okay. Just the instructions, not surprisingly, are not straightforward. Yes?
Can you do, or be in the right direction for 1.3, number 13?
Oh, looks like I was thinking about something here. 2 3x3 matrices with the same column space. Oh, equal, okay. So the first thing about this problem is they want both of those matrices to have the same column space, meaning, and that column space is the plane of all vectors perpendicular to 1, 1, 1. I don't know what that scribble is related to, 13 or 14. Oh, it is 14, okay, 13. How would I find a vector perpendicular to 1, 1, 1? Well, it's got to be true if two vectors are perpendicular to each other. Their dot product is 0. So you can see the little scrabble I did. If I say the vector I want is ABC, what's ABC dot 1, 1, 1? A plus B plus C, yes? And I want that to be 0. So what do you use for ABC? Anything that works. If, I want you all to be with me here, right? The dot product of ABC and 1, 1, 1 is A plus B plus C. If you pick any frickin' numbers for A, B, and C, making it 0 when you add them, you found a vector perpendicular. You had to, yes? Because the dot product is A plus B plus C, and if you make it 0, they're perpendicular. Can you come up with any numbers besides 0 for A, B, and C so that their sum is 0?
1, negative 1, 0.
Do it again.
1, negative 1, 0.
1, negative 1, 0. Kick ass. So that would be one column in one of your matrices. You see what I mean? And then you just keep going. Make another one, make it a column. Make another one, make it a column. You need 6 of them for your 2 3x3 columns, or matrices. Is everybody with me? So that's what they mean. That would force the column space. Now you have to be careful. If I want the column space to be the plane of all vectors, each vector that I put in, has to be, all the vectors have to be linearly independent from each other, yes? So as you go, you gotta make sure whatever numbers you pick for ABC, it's linearly independent with what you already put in, yes? Okay, so this problem, of course I would love this problem. Because the first sentence has got a huge amount of work. Look at me laughing at your play. And then it says, what is usually, and this is the part that I could probably do without, and you probably could too, is Trey. He's very loose. What is usually the column space of A plus B? So it depends on what you picked, but you have to think more generally than what you picked. But if you pick things in a more random way, you should probably see what he wants you to see. So one vector that you all could use if you want to is 1, -1, 0. Pick something else that is different from that, right? Couldn't you pick something for all three and still make it 0? Like 2, -1, -1. Is that independent from the one we just said? Yes, because they're not multiples of each other. Now the tricky one is going to be the third one. You want to make sure that it's independent from those two.
Do the vectors in A have to be independent from B?
They didn't say. They didn't say, but if I were you, I would. At least pick one vector that's different. So maybe you only need 4 vectors, yes. And make sure that the other one is independent. Do you see what I mean? If you make that matrix B the same as A, then you're not gonna get the usually answer, because you're gonna be doing something that's unusual in terms of random chance.
Yeah.
Okay. Does that make more sense, at least what they want you to do? Who asked that question? You asked that question?
Yeah.
Okay, that at least makes more sense in terms of even just what they want you to do.
Yeah, I think so.
Okay. That one's trippy. So guys, I don't know if you know this, but I'm very aware that some of the homework problems are trippy as hell. Yes? Therefore, if I don't hear any questions about them, I'm like, oh, well, everybody's skipping that one. So do you understand what I'm trying to tell you? They are trippy. There are trippy ones. There are easy ones. There are ones in there that are so easy that you make more out of them, and I don't blame you. Because you're like, that can't be that easy, it must be something more. He will give stupid easy problems. And then the next problem will be this crazy, yes, I understand, I know this. And yet I still want you to do homework, But I just want you to feel comfortable. You can ask. They're weird. It's weird shit. Right? I do like that if you do enough of the homework, you will have played with the ideas from several directions. And that's the best way to understand an idea, is to look at it from several perspectives. And that's why anybody who tutors knows their math really freaking well, because if you explain it to somebody, they don't know what you mean, you have to come up with a whole different way to look at it, to explain it to them again. So I highly recommend becoming a tutor if you want to do any further math. Anything, it's wide open, guys. Wide open, yes.
Can you go over an A equals LU problem?
Yes, okay, good. Let me do this. I normally don't give this out too early, but let me go ahead and give you the answer key. Before I give this to you, so this is the answer key for the practice test. If you did not try the practice test, do not do this. Yeah. I would have done that. Right? Because that'll build false confidence. It's so easy to agree with me instead of doing the problem. So, dear God, if you don't try the practice, and you don't have to, you never have to try the practice test. You could have already thrown it away. Do the same thing with this then. Because if you look at this, you're just going to get false confidence. Yes? Okay, here we go. But I do want to point out on the second page here, there's an A equals LU example. We'll do another one fresh. But there's 2 pages, by the way, so it's going to take me a little while. Sorry. Like one semester, somebody asked me if I handwrote all of these. Like, yes. I can't do that. Got in trouble. Showing up in this. So there's one of each. So take one, pass the rest down. Take one, pass the rest down. pages, yep, there we go. Pass one down. Wait, you mean the inverse thing you just said a minute ago? So the inverse, the augmenting with the I. It works for every invertible matrix. Now some matrices are not invertible, in which case you'll end up with a weird zero row of nothingness. Okay, so on the second page of the answer key, I've given my attempt at a color-coded A equals LU factorization. There are other methods to factor. This one's a little bit trippy, but once you see the pattern, you can do it with any size matrix, and it goes relatively quickly. So what I try to show you is I first think I want multiples of the first row that will kill all these things. So you're trying to get zeros and zeros.
Oh, so you're trying to make the first row and first column all 0?
Yeah, I'm trying to make this zeros and this zeros.
Okay.
So if I multiply this one by 1 and subtract, it's beautiful. If I multiply this one by 3 and then subtract it from here, beautiful, yes?
So wait,
So I am playing with 1, 2, 3. What do I multiply 1, 2, 3 by? So that when I subtract it, I get zeros.
1.
1. What do I multiply 1, 2, 3 by? So that when I subtract this row minus it, I'll end up with a 0 first. 3.
So that's where the 3, 6, 9 comes from.
Yep. 3 times 1, 2, 3 is 3, 6, 9.
Okay.
How do I kill this negative 2? I subtract negative 2, so I must multiply this by negative 2, negative 2, negative 4, negative 6.
Got it.
The one thing that's different, I want you to realize, this is exactly what we do when we row reduce, isn't it? The one thing that's different is we normally don't put zeros like this. The only thing that's different is we would normally keep 1, 2, 3 right there, yes? Otherwise, it's exactly what we would do. And the only reason that this method does that is so that it really focuses your attention on what's important at the moment. Because then I'm gonna now rewrite it, and now I'm gonna focus on this.
You want to eliminate.
What do I multiply this by so that 0 minus it stays 0?
0.
0. What do I multiply this by? 1, so that it subtracts itself, I get zeros.
Yep.
And what do I multiply this by? So that I would subtract this minus it, I end up with a 0 here.
1.
Negative 1.
Oh, I see.
Because negative 7 times negative 1 is 7. 7 minus 7 is 0.
Yeah, and then
Now notice, let me go back. 1, 3, negative 2. That goes here. 0, 1, negative 1. That goes here. So what makes the L matrix are all the multipliers you needed. Yes? Let me stop for a minute. And what makes the U matrix is each thing you're focusing on. What were we focusing on at first? 1, 2, 3.
Yeah.
Now what are we focusing on? 0, negative 7, negative 10. Now what am I focusing on? 0, 0, negative 7. And, it's kind of funny. In fact, this kind of makes sense. If I want a truly lower triangular thing, this should be 0, 0. And in this case, this will always be 1. And it makes sense, because what am I going to subtract from this to make it 0? Itself. So I'm going to multiply it by 1. I love you guys. That is trippy. And then I verified it, and you can verify it also. So make sure you know how to multiply two matrices. I'm going to have you do that at least once. Not with an 8 by 8 or something insane, because then it's just the same thing. Okay. Will you be able to use your calculator on some of the matrices? Yes. Can you use it on all of them? No. Now, that is how to get LU. To make this into a computer program is easy as shit. And I don't care how big the matrix is that I feed it, I just give it the end time and it'll just keep going. It'll just keep doing the same thing over and over, just keep going until it's done the whole thing. And it's keeping track of this and it's keeping track of that. And again, I understand that not all of us are in for computer science related fields, but a big part of linear algebra is in that bend. It's kind of like the math that we do, how can it be better put into algorithms for computers to utilize and be efficient? That's a big part of it. It's not all of linear, thankfully, obviously. I didn't say thankfully, though. That's kind of mean. I like computer science, but oh, too bad. All right. So you want to do another one fresh? Yes? Okay.
So you try and eliminate the first column, first row with the number.
You kind of keep moving in,
Yeah.
because now I want to eliminate the second row,
The
second column.
And then eliminate.
And then I finally want to eliminate the only thing left. So do you see how this is always going to be 0, 0, 1?
Yeah.
Because I'm always going to multiply the last one by 1 to kill it?
And the U will always be 1, 0, 0 for the first one.
Yes. Okay. Okay, this is exciting. So why don't we, all right, yeah, Jeff, look at this. It's the same thing all the way down, Jeff. Okay. Why don't we do this? There's a few different ways I can do this. Okay. We could start with an L and a U, multiply those together, and then do the LU process because we already know what it's supposed to be at the end. Does that make sense? Which is kind of the way I sometimes create a problem is I start with where I want it to be. Because if I just make up an A right now, will it necessarily be good? Will it necessarily be invertible? Because do you guys understand the next step after this is what do you use the LU business for? Yes? It's like, ooh, I made it. Good job, everybody. But what do I do with that? I don't know if you guys remember what that actually does for us. So obviously, for this example, we'll go one extra step. I'll show you what it's useful for. So let's do this. I made an executive's decision because let's pick an L. So all it needs to be is lower triangular. And what does that mean?
It means that the zeros are at the top.
Zeros are up here. So just give me whatever you want here. Somebody give me a number.
7.
7? Neat. You guys say the same thing?
9.
12? Sure, why not? I love you guys. 800, shut up. Now I want an upper triangular. So that's going to have to, now it doesn't have to have ones down here from the way the process works, but it needs to have zeros here. Give me a negative number.
2.
Negative 2? Okay. Now somebody else give me a positive number.
5.
5? Okay, sorry. Somebody else give me a positive number. Who?
9.
9. Okay. And somebody give me a negative number. Negative 3. Somebody give me a negative number. Negative 13. And then somebody give me, and then I'll give myself this one, damn it. Okay. All right. So, you all agree that's lower and upper triangular? Yes? Okay, so. Do you see how I multiply these together? Won't be as bad as it could be because there's a whole bunch of zeros. So let's see if we can multiply this. Put this A back together. So I get, so this is going to basically recreate 5, 9, negative 3, yes? Which kind of goes along with what we just did. And then this is going to make 35 plus 0, is that cool? 63 minus 2. Oh, God. and then negative 21 minus 13. Are you guys all with me? Okay. You have brought this on yourselves. And then I get 45, right? 0, 0. And then I get 81 minus 24 is something, 57. And then I get negative 27 minus 36 plus 2. Negative 27 minus 36. Is that negative 59?
Negative 61.
Negative,
Question mark?
what did I say? Negative 27 minus, what did I say, 36? Look at me being all hopeful. Negative 27 minus 100 and, what is that? 50, no, 156? Is that 12 times 13?
Yeah.
Fudge. All right, and then plus 2. I love you guys so much. So then you get negative 183 plus 2, negative 181. If it's wrong, we're screwed, but that's all right. Let's see.
That should be right.
Sounds about right. Yeah, I think it's right. Okay. Yes, now. Oh, look at that. That's yummy. Ooh, that's yummy. Okay, here we go. Oh, man. I'm so much nicer than you guys. So, can somebody tell me the first step? The beautiful thing about this process, by the way, is you're not going to get fractions. You're not going to, well, let's see. Maybe we will here. We'll see. We shouldn't, but you could, I guess. All right. So if I take this matrix, what am I focusing on at first? Oh my God. I gotta be careful with everything being so big. First row, first column. Yeah, I'm gonna kill those. So what am I gonna multiply? So I'm gonna focus on the first row, correct? And I'm gonna use multiples of it to kill the first row and the first column.
You're seeing a negative on the 3.
I probably am. Yes, thank you. Dear God. Please, dear God, help me out. Okay. So obviously, do you see how this is always going to be multiplied by 1?
Yeah.
Because if I subtract itself, believe it or not, it kills itself. What do I want to multiply this by so I can kill the first piece of this? 7. Holy shit. So I'm going to multiply by 7, and I'm going to multiply this by 7. 5 times 7 is 35, 9 times 7 is 63, negative 3 times 7, negative 21. No C, Jesus. And then what am I going to multiply this one by to kill the 45? 9. So that'll be 45, 81, negative 27. Let me stop for a minute. By the way, I mean, the book hints at this process, but it doesn't show you this process. I have no idea if any of you have tried to look at that section yet. So again, do you guys see what we're trying to do? We're actually trying to strip away multiples of the first row to kind of leave bare the bare bones of the other things. That's kind of why this process works. If I collect the multiples that make that happen, I know how to put it back together. So I'm keeping track of how I'm tearing it apart so that when I multiply back out, I put it back together. That's the idea. Okay, so now we subtract. And not surprisingly, we get zeros everywhere we force there to be zeros, yes? What is 61 minus 63? Negative 2. And what is negative 34 plus 21? Negative 13. Is anything already looking familiar 2 times over? 179. Does that look familiar?
Yeah.
How about 0? How about 5, 9, negative 3? How about 0, negative 2, negative 13? Yes? Love you guys. Okay. And then here, I'm sorry, we got one more thing. 57 minus 81.
Negative 24.
And negative 181 plus 27. I think that's right.
Yes. Negative.
Is it?
Negative,
No.
negative 154.
54. Dadgummit. Okay. So this would be the first column, and it is, and this would be the first row, and it is. This would be the second row, and it is. So basically L is a collection of your columns, and those columns are the multiples. U is a collection of the rows you're focusing on at each step. So I focus on the first row, kill shit, then I focus on the second row that's left over. Yes? Okay. So now if I rewrite this, I got 0, 0, 0, 0, negative 2, negative 13, 0, negative 24, 154.
It's negative 154, right?
Of course it is. Yes, it is. Thank you. Minus, now what do I, now I'm going to focus on this row. What do I multiply it by to keep the zeros?
0.
0. What do I multiply by to kill itself? 1. What do I multiply by
12.
to kill this guy? 12. 12 times negative 13 is 156. So 0, 1, 12. 0, 1, 12, yes? And of course I already pointed out 0, negative 2, negative 13, 0, negative 2, negative 13. And what do I get? I get 0, 0, 0,
0, 0, 0,
0, 0, 0,
0,
0, 0, 2. So that would be my last row. And my last column is always 0, 0, 1 because I want none of these, one of those. Trip it, trip it, trip it. Okay. I don't want to use this one. I'm going to use the one from my example, damn it. I don't want to use this one. So, where did I put those papers? Dadgummit, I just had it. Oh yeah, I'm on the back. Okay. Let's go back to this guy. Okay, let's go back to this guy. You guys with me on that one a little bit? A little bit? A little bit? Thank you. It's a one option of several, but compared to other things I've seen, this is much better. It's not like anything you've seen before, but to be really honest, you guys understand elimination decently? Hopefully you do, because otherwise you're screwed. But if you understand elimination, then all this is we normally leave the first row alone, like right here. We would normally leave the first row alone. This process just says no. Subtract it from itself also. Yes? That's really the only difference with every step we're doing. Yes?
I have a fun question. Is the last column always going to be 0, 0, 1?
From this process, yes. So then that begs the question is, does this process lead to the only real way to do this LU factorization? Is there only one way to do the LU factorization?
No.
We'll see later. For right now, this is the best process to do this. Okay. Okay. So what I want to do right now is, like I said earlier, I want to show an example of how this helps. And again, if you guys really want me to have you do a problem where this really, really will make things quicker than it would have been otherwise, I will give you a 12 by 12 system of equations. Yes? So we're doing 3 by 3 because I don't believe in busy work for the sake of busy work. But the gains we would get are minimized then. This is scalable. This whole idea is scalable. So if I have a larger matrix, it will make the whole process quicker to do this than to just do these systems of equations like we normally would. More importantly, in a way, making this into a subroutine you can call, independent of how big the matrix is. Just whatever how big the matrix is, it just has a place it knows to stop. So it's built in. So just crank it out. It will be very efficient. Much more efficient than just feeding in a matrix and having to do Gaussian elimination. It would be much more efficient. Okay, maybe. And efficient, I mean, runs quicker. Okay. So let's say my problem was, bless you. I want to solve this equation. What you got, Jeff? I don't know, Jeff. Didn't you have some? I did have something, but I don't know what I did with it. Say again?
Where'd you take the inverse of sulfur x?
Take the inverse of what? Sorry.
Of a.
No,
No.
not right now.
Okay.
That's a separate thing we could do. I just wanted to give something that was semi-decent here. But let's see. Can you come up with something real quick, Jeff? I can, but it would be boring as shit. So let me think for a moment. All right. Negative one. So this is 1. This is 6. Oh shit. Is 2. Okay. Now, real quick. Do you guys have any sense of whether or not these are independent, these columns? Do you guys have a sense of if these are independent? You should, because one thing I could look at, if you want to, if you have no other questions, we'll try to do the LU business with a non-invertible matrix. Do you guys see what I mean? Something weird should happen. Because one reason we do the LU factorization is to make solving this equation easier. And when might this equation not actually have an answer? If A is not full rank, meaning A is not invertible, yes? So then your question really should be, if you're curious about this at all, what would LU factorization do if my A was freaking non-invertible to begin with? What weird shit would happen? Yes? Okay, but again, I don't want to waste time doing that if people have other questions, because there's going to be a lot of other stuff on this test besides this. So we know the LU factorization for this. Where'd it go? There it is. You copy that down here. Okay, so this is that earlier one we did, yes? So this is LU. So then the equation becomes, we write it like this first, LUX equals B, yes, where this is B. I love this. So many guys have looked at me like, you have not made sense one day in here, man. Oh well. Okay, so we factored A. This is A, yes? This is A. Right here, this is A. So this is AX equals B. We factored A as LU. So now I can write it as LUX equals B because A is LU. Okay. What would U times X be? Tell me anything about U times X. It's a vector, kick ass. That's all I wanted. I would have taken whatever the hell you guys said. We would have eventually got there, and this man's like, just freaking tell you right off the bat. You guys agree? U times X would be a vector. Yes? Because how big is U? 3 by 3. How big is X? 3 by 1. So 3 by 8 times 3 by 1 would be 3 by 1. So it's a vector, correct? So I'm just going to call it. Do you guys remember this now? I'm just going to call it Y. So this becomes a 2-rank thing. If I can solve for Y, then UX equals Y, I can solve for X. Bless you. Now again, bless you. Bless you. As humans, bless you. As humans, this seems a little silly for 2 reasons. Again, I'm not going to give you 12 by 12, but if I did, the work would be a little longer than it is now, but it would be nowhere near as long as trying to deal with that directly. Okay. So let's see. L. So now we're going to focus on L times Y. If I can figure out what Y is, then UX equals Y, and then I can figure out what X is. Because what's the whole point of this equation? What am I trying to figure out? X1, X2, I'm trying to figure out the X vector, yes? Okay, so just kind of doing it in 2 steps. So what was L again? This guy here. So can you guys see anything right off the bat?
It's an elementary matrix.
Well, no. Elementary matrices officially only have one thing they do, but can you tell me an answer? Huh? Sure, yes, yes. But tell me an answer. Y1 equals 1, thank you. Okay. So you can call it all these kind of shit. I don't care if you don't know the name. Just right off the bat, you know Y1 equals 1, yes. 1Y1 equals 1. So Y1 equals 1. What's the second thing say? 3 Y1s plus Y2 equals 6. Do you guys see that? So then what's Y2? 3. Crazy. And then what's the last dude say?
-2 times
Y1 times Y2 is 3 plus Y3, right? Bam, bam, bam. Equals 2. So what's Y3? 7. I like it. I love you guys. So we figured out Y. What is Y equivalent to in the first parts of the problem? UX. So now I do exactly what I just did. U is 1, 2, 3, 0, -7, -10, 0, 0, -7, x1, x2, x3 equals 1, 3, 7. What do you know right off the bat? x3 is -1, and then you get -7 x2 minus 10 x1 equals 3. Does everybody see where I'm getting that shit from? Just looking at this, no x1s, minus 7 x2s, minus 10 x3s. -7 x2s, minus 10 x3 is plus 10. So -7 x2 equals -7, x2 is 1. Calm down, I'm sorry. And then the first guy tells me what?
x1
x1
plus 2 minus 3
plus 2x2 plus 3x3 equals 1. So x minus 2 equals 1, so x is x1, sorry. 2. So what's my answer?
2
2, 1, -1. Kick ass. Vector. That is the vector that I would feed to A, and it would spit out B. Wouldn't you agree that that's nice, because like somebody did point out, this leads to 2 back substitution situations, and back substitution is the easiest shit in the world. And wasn't the stuff we did to get Y very similar to similar to the stuff we did to get X? All the work we did to get the Y's, didn't we start off with, I know this one, and I know it, so now I know the other one? Yes? Isn't that exactly what we did here, except we started at the bottom, went up? Do you see how you can very easily program, make a program to do that, to run up and down, however big your matrix is? So everything we just did is scalable. Obviously, if I have a bigger matrix, everything we just did is going to be a little longer, but nowhere near as much longer as if you're just doing pure Gaussian elimination all the way. So if you want to, we can focus on something else. I don't know if you guys all tried the practice test out, but if you're looking it over right now and something doesn't make a damn bit of sense, you can ask me. We can talk about it. If you have anything from the quiz, we can talk about it.
For the problems on the practice test that require explanation,
somebody earlier, about some of the homework where I was just like explaining. I very often just need a little bit so I can clue in on your thought process. So some people, you can sometimes get the right answer for the wrong reason. If you give me no reasoning, number one, you might be happy because then you won't lose any points. But number two, I will never be able to correct that mistake. And then maybe it'll come back in a big way later. Does that make sense? I have no way to answer that question. So if you want to be over careful, you can give me more. I normally don't need a ton. I just need enough to see that you're thinking about things correctly. Capture what you're doing in your head, write it down if you're doing something in your head. Yeah? There's no answer to that. Okay. I definitely don't need a page full of explanation for every problem. Just need a little something. By the way, just so you know, the next chapter we're getting into is going to finally kind of make a more complete picture, because I've mentioned null space a couple times. You guys remember that? So that's going to come into play so we can see how together that makes a complete picture. Because if my column space is less than the full thing it could be, what happened to those other dimensions? That's a good question. Do those other dimensions do anything for me? Do they mean anything? Yes? Yeah. A equals B?
Yeah, but if, like one row is all zeros,
Oh, all right, let me make sure. A equals LU? No.
like on one of the quizzes, or no, it was when we were doing the practice for the quiz, we had like a, you know, like a way to get the column 3, but someone gave up an answer at, and we talked after the class.
Oh, yeah. Okay. All right, good. I keep forgetting to come back to this thing, because I was being really silly. Let's see, where is that? Here. Okay. I was so freaking focused on column space. Okay. So let's take a step back here. I was so focused on column space and you guys creating straight from the columns something that made 0. And I had a different matrix that it was kind of easier to see. Forget all that shit. What does the R tell me? What does the 2 mean? In fact, that was a question on the last quiz, if I remember correctly. What does that 2 mean exactly?
That's 2 times rows, multiple 2.
People are saying rows, I don't understand that.
Columns are 2 times
Okay.
columns.
So to get column 2, you would double column 1. Yes? And this one means
3 rows.
to get column 4, you would take
3 rows.
3 column 1s
Plus 3.
plus a column 3. Yes? Do you guys see that? All right, maybe we should just focus on that for a minute. Okay. Where are my leading ones? So the first and third are the matrices that would go into my column space, my column, my C. I'll never know what the hell to call it, just C, right? C is a collection of all my independent columns. The other columns are telling me how do I create, so the numbers left in the other columns tell me how do I take those 2 columns, because remember, what did I just say? Those are the 2 independent columns. Aren't they the ones that make everything else? If you're dependent, you must be some multiple or combination of those 2, yes? All right. So the second column comes from doubling the first, and that's easy to see. The fourth column comes from 3 times the first plus 1 times the third, yes? Because I established 0, 1, 0, 0 is related to the third column. Let me stop for a minute. Because how would you, if you're looking this way, how would you construct these numbers? When you do 3 times this plus 1 of these to make this, yes? What's 3 times this? 3, 0, 0, 0. What's 1 times this? 0, 1, 0, 0. What do you get when you add those? 3, 1, 0, 0. So if I take 3 the first column plus 1 the third column, I get the fourth column. Does that check? 3 plus 4 is 7. Negative 3 plus 2 is negative 1. 6 minus 1 is yes. Yes? Okay. I really want to make sure we're all there. Okay, we're all there. Good. So what I wanted to do was eventually put that back to it when we focused more on that. But at first I was trying to get us to get just multiples of the columns. And it was a little harder just to see it. But if you look at this now, it's easy as shit. How do I... All right, let me just do this. What if I took none of these columns, let me write it like this. What if I took 0 of this one, 0 of that one, negative 1 of this one, and 2 of that one? What would that make? If I took 2 of the first, negative 1 of the second, none of these, none of these,
0.
that would make zeros. So that is one vector that I can multiply A by, and it would make the 0 vector. Yes? And the whole point of that little piece was, if A is not full rank, if A does not have, all of its columns are not linearly independent, there has to be an infinite number of vectors that I can multiply A by and get 0. Why? This is really silly. This is dumb. If there's one vector that's a multiple of another one, if I just add multiples of them together, make everything else 0, of course I'm going to get zeros. In this example, look. Twice the first dude minus the second dude. Of course that's nothing but if I 0 the other ones out. Yes? No? Maybe? Screw you? Okay. Can anyone come up with a different one that has no zeros? I think one dude did. If I make this 1, 1, 1, negative 1, something like that, right? 1 plus 2 minus 3 is 0. 1 minus 1 is 0. Do you guys see that? 1, 1, 1, negative 1. Yes? Wouldn't that make nothing but zeros? Okay, so take A, everybody, do this. Take A. You know, like, I'll take an A. No, shut up. Take matrix A and multiply it by 1, 1, 1, negative 1. Do a couple to see. Yes? Help me out, how do I multiply these? We can do row picture or column picture. Row picture is the one we do traditionally. So I would take that dollar that. That's 1 plus 2 plus 4 minus 7 is, of course, 1 plus 2 plus 4 minus 7 is 0. Negative 1 minus 2 is negative 3, plus 2 is negative 1, plus 1 is 0. Yes? I mean, I'm going to get zeros because I designed it to make zeros. So what if I do 2, 2, 2, negative 2? Yes. So off of just this vector, how many vectors can I create to make 0 vector at the end? Infinite. I can just multiply by whatever constant I want to here, yes? And even on top of that, I have this whole family of vectors, because I can have 2, negative 1, 0, 0, 4, negative 2, 0, 0, negative 2, 1, 0, 0, blah, 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 blah. And then you can do a combination of these things. What the shit? Okay. So that, by itself, is something we need to understand right now, is that. Eventually, that will feed into my null space. Because what are we creating from these vectors? 0 outputs. So doesn't that make sense that those should feed into the null space somehow? The null space should be the space that makes null, that makes nothing. Sounds like when a nihilist dies, is where they go. The space of nothing sounds fantastic. Okay. Maybe that's where they live, actually. I don't know. Is that okay? Does that basically answer your question? I'm pretty sure. Yes? Whoever asked that question that got me off on this stuff. Hello? Did they leave? Hey, you got it? Okay. All right. So guys, let me ask you this question. Well, I don't know. Maybe you're all just very quiet. But I'm always concerned I'm not approachable. I'm not somebody you feel like you can come to with questions. If that's true, I'm sorry. I don't mean that to be the way it is. I really don't. I hope that isn't true. I am open to questions. This is weird shit. This is weird. Is this like any other math you've ever done? If you've never seen any linear, is this like any math you've ever done? I would say no. Right? Your calc 1, calc 2, calc 3, differential, all that shit just kind of bleeds into each other. You're like, it's the same, it's the same. And then suddenly, this, and I talked to my diffq students when I taught diffq, and I said, have you taken any linear? And I said, diffq is like this. How many guys have taken diffq, differential equations? Anybody? Would you agree that diffq is this? Boom, boom. It's very recipe-ish. If it looks like this, you do this. If it looks like that, you do that, yes? And that's very much what you feel like. This class is, you know, it's just, it's less, bam, bam, bam. It just isn't. I try to make it bam, bam where it makes sense, but it's not always that. So, I don't know how much more I can say to get you to understand this stuff is weird. It is weird. So if you're having trouble with the homework, that's fine. But go get help. Yeah. Yeah.
Number,
Yeah, like, let me shut this guy.
number 27 and 2.2.
2-2? 27. Okay. This one?
Yeah.
Oh yeah, so, okay. Has anyone tried this one out yet? Number 27.
Yeah.
Did you find where they described this?
Which one is that? 2.3 or 2.2?
2.2, yes? 27, yeah.
Nope, that's 2.3.
If I remember correctly,
This one. 27.
it's something they say.
Oh, it's like. Oh, I kind of viewed it as where, like the 4 times I 4.
Yeah, I think
was
he's
like the identity matrix,
yeah.
right? And then I think the -1s is like a 4x4 all ones.
Yeah, but somewhere he actually defined what he
didn't
meant
read-
by this.
I didn't read where he defined it. That's just what I assumed.
Oh man, it might be in something else I've seen.
But the answer is like
I've
it's
seen
not
where he's
vertical.
talked about I and I's. Alright, let me see. I don't think he's put it back here. Nope, okay. Just somewhere he mentioned it very quickly, and then he uses it like it's this major thing you're supposed to know. Alright, I'm not gonna find it quickly, am I? No. Did he do it here? No. No, okay. That's chapter 1. Okay. So 27. So if we assume him being a little cheeky and saying I like the letter I, okay, so let's see if we can break this down. even that doesn't make sense. So 4 times I would be, like, for example, for a 3 by 3 would be this. That would be 4I, yes? Now, this little 4, I guess, oh, okay, I see, maybe I see what he means. I think maybe he means 4-dimensional. What is happening back there? Okay, that might be what this 4 means here. Minus 1s, okay, so minus the 4 by 4 that's made of 1s. This feels familiar, but I can't remember for sure. Show that that is not invertible. So what do we get here? We get 3, -1, -1, -1, -1, -1, 3. So it's going to be 3, 3, -1, -1, -1, negative. Did I go too far?
No.
No. There. It's going to be that. Woo! Seems right. Okay. So if I've interpreted that correctly, which I'm not 1,000% certain about. Okay, how would I show, if I gave you a matrix, how could you show it's not invertible? You could look at the determinant. I really don't want to look at the determinant of 4 by 4. But you could. If you want to do it very directly, you just have to find one column that's dependent on any others. Yes, any combination of any others. Yes? You could start to row reduce it. Yeah, you could row reduce it to try to show it, right? If you throw that in the calculator, does anyone have the calculator? Yeah. So this would be one that I would let you go ahead and see if you can row reduce it. I'm not 100% certain I've interpreted his weirdness correctly. Let's see back here. Does it say anything? Oh, are there answers back here? No. No? Okay, neat. Well, here, let me do this. Look at this real quick. It's kind of silly. What is column 1 plus column 2 plus column 3 plus column 4?
0.
Yeah, it's all zeros, right? Okay. Which means that one of them is a combination of the other 3, right? If you have 4, if you have any vectors that add to be 0, that means you can solve for one of them and it equals a combination of the other 3, yes? So column 1 would equal negative column 2 plus minus column 3 minus column 4. Therefore, is this invertible? No, okay. So that's the first thing we should look for is, if I just try to